Our next speaker is Hassane Hamdaoui from the Department of Physics and Astronomy, and he will be presenting Light Under the Spotlight.
Thank you. Yeah. So light is basically everywhere, and light is also the source of all the life in our planet. And thanks to light, you can see all the awesome and cool objects that we have in our planet Earth. And how that is happen is actually those objects reflecting light into your eyes. But did you ever wonder if light can see light? Or in the physics world, can light actually interact with light? So the simple answer to this question is yes. But now you are probably wondering, but how? There are actually many ways light can interact with light, and I will only talk about, I will say, the cool and the awesome one, which is also the simplest, which is light by light scattering. And this process has been predicted like 90 years ago and remained unobserved till now experimentally, because it's so challenging experimentally, because the probability of such process is so small. And now I'm going to walk you through this process. It's pretty simple. So you have two photons, which are the particles of light, going into each other or colliding into each other through this red box that can contain other charged particles like electrons that you know of. And this will induce or produce two different new photons, which I call photon 3 and 4. This process is so important because it's predicted by a theory that we actually use in a daily basis as a particle physicist. But it still remained unobserved. And another thing that why this process is important to us is that inside this red box, we can also have particles that have not been discovered yet, like dark matter candidate. So it's really important to measure this process. And to do so, the simplest experiment that you can think of, why don't we collide just two laser beams and see what happens? Well, I can tell you that many people have actually tried, and it didn't happen because this process have this small probability. We don't have powerful enough lasers to do so. So what I'm going to show you today is an alternative or an unconventional way to actually measure this process. And it all happened in the Large Hadron Collider. And what's the Large Hadron Collider? You can think of it as when kids are playing with their toys and they get bored, they will end up breaking them, and that's just them being particle physicists. Do you want to break the toys to actually understand how the toy works? And that's exactly what we do in the LHC. We break particles to understand what are made of those particles and how those components actually interact to each other. Here is a more realistic picture of the actual machine. It's a 27-kilometer circular collider with 4 big experiments. The one you can see here, and mine is Atlas. It's really the largest machine in the world for now. What we collide or what we accelerate inside this tunnel are two kinds of things, usually. So we have the protons, which we take from the hydrogen atom, and you might have heard about this one. The protons are the one that we actually used to discover the famous God particle or the Higgs particle in 2012. And we also collide lead ions that we just use lead atoms and remove the electrons, and we are left with a lead nucleus. And the lead nucleus is made of protons and neutrons. So the protons, as you know, are electrically charged, so they create this huge electromagnetic field around the lead nucleus. And this field is actually the key for this particular observation. And now you are wondering why, because this field actually contains the photons, the photon number 1 and 2 that I mentioned in my previous slides, which will induce this particle interaction. And this lead nuclei is typically accelerated to almost the speed of light inside the tunnel. And we use our detector as a camera to actually look at the collision. So typically, when we collide these two lead nuclei, we want them to actually interact heads-on. But it happens sometimes that they don't do so. They will just pass near each other, and they will only interact via this electromagnetic field. And by doing so, they will induce this photon interacting with another photon, which are the two blue photons here, they will interact with each other and produce the two photons, which I named photon 3 and 4, which we can see inside our huge Atlas detector. And this is what a light bylight scattering process looks like. To summarize, we actually looked at 14 billion collisions from our detector, and we've been able to observe 59 events. Thank you.